Assalamu alaikum. How are you, everybody? Our lesson today, Chemistry, Chapter 10, Section 4, Change of State, Part 1. The objectives of our lesson: to explain the relationship between equilibrium and the change of state, explain what's meant by equilibrium vapor pressure, describe the process of boiling, freezing, melting, and sublimation, and interpret phase diagrams. In the previous sections, we discussed the three states of matter: gases, liquids, and solids. Today we'll discuss the change of state between them. And we know that from our previous study that a solid can change into a liquid. It's called melting, like the melting of ice into water. Solid can change into a gas directly without liquid state, like dry ice. It changes into carbon dioxide gas. It's called sublimation. Carbon dioxide has no liquid state. It changes between solid state and gas state. Liquid can change into solid. It's called freezing, like changing of water into ice, the freezing of water into ice. Liquid can change into a gas, vaporization, like water into water vapor, or liquid bromine to vapor bromine. Gas can change into a liquid, called condensation, like the condensation of water vapor into water on cold surfaces. And gas can change into a solid directly without passing by the liquid state. It's the opposite of sublimation. Like water vapor can change into ice, or carbon dioxide gas can change into dry ice directly. This is called deposition. So melting is the opposite of freezing. Sublimation is the opposite of deposition. Vaporization is the opposite of condensation. A change of state and equilibrium. First, what's a phase? A phase is any part of a system that has uniform composition and properties. It's equal to state. We can say that liquid state or liquid phase, gas state or gas phase, solid state or solid phase. A gas in contact with its liquid or solid phase is called vapor. So vapor, it's a gas. In contact with liquid or a solid, it's liquid or it's a solid. Like the gas state of water while boiling, it's called water vapor. Here, the distribution of molecules in a liquid at different temperatures. Here at a lower temperature, what do you observe here? Most here the relation between number of molecules and kinetic energy. Kinetic energy increases, and here number of molecules increases. You notice that most of the molecules have less kinetic energy in the low temperature. If the temperature increases, the number of molecules that has more kinetic energy start to increase. So here at lower temperature and here at higher temperature. Here the minimum kinetic energy required by the molecules to escape, to change into a gas. If the molecule has less kinetic energy, it can't escape. More kinetic energy, it can escape in the gas state. So for the molecules to change, to escape from the liquid state to become in the gas state, it needs a minimum kinetic energy. If you have a flask here, this flask containing a liquid. At the beginning, no, here in the liquid state, no molecules escape now. The molecules here in figure number 2 start to escape, and some molecules start to fall down to the liquid. but the number of molecules that escape larger than the number of molecules that fall down to the liquid state. So here, no equilibrium. Number of molecules that can escape more than the number of molecules that fall down. For example, if 100 molecules can escape in a second, for example, from the surface of the liquid to change into a gas, and the number of molecules that come down to the liquid state equals, for example, 50, 60, so this is not the equilibrium state. Here, equilibrium is reached. Means what? The number of molecules that escape from the liquid state to the gas state equal the number of molecules that fall down to the liquid state. For example, 100 molecules in 1 second change from liquid to gas, and 100 change from gas to liquid. Here, equilibrium is reached. Okay, clear? So, in a closed system like this one, closed here, not open, the rate of condensation equals the rate of evaporation, and state of equilibrium is established. Okay, rate of condensation equals rate of evaporation. This is called equilibrium. Equilibrium is a dynamic condition in which two opposing changes occur at equal rates in a closed system. So this is the meaning of equilibrium. So equilibrium means a dynamic condition. Dynamic means changing, not static, not fixed, in which two opposing changes like condensation and evaporation occurs at equal rates in a closed system. Vapor molecules in equilibrium with a liquid in a closed system exerts pressure proportional to the condensation of molecules in the vapor phase. Here, the molecules that escape exerts a pressure on the liquid, and also the liquid exerts a pressure on the gas. So here equal pressure, and we reach equilibrium vapor pressure of a liquid. What's equilibrium vapor pressure of a liquid? It is the pressure exerted by vapor in equilibrium with its corresponding liquid at a given temperature. Okay, it's the pressure exerted by the vapor. The vapor exerts a pressure on the liquid in equilibrium when the state of equilibrium is reached and corresponding to liquid at a given temperature. The equilibrium vapor pressure increases with increasing temperature. If you heat the flask, what will happen? More molecules will escape. So they exert more pressure and more molecules will fall down. So more molecules, increasing the temperature of the liquid, increases the average kinetic energy of the liquid molecules. So more molecules can escape. More molecules can escape, more pressure is exerted. So the equilibrium vapor pressure increases with increasing temperature. And each liquid has a specific equilibrium vapor pressure at a given temperature. Alcohol different from water, different from any other liquid. All liquids have characteristic forces of attraction between them. Why? Each liquid has a specific equilibrium vapor pressure due to the attraction force between the particles, between the molecules. Some liquids, we call them volatile liquids that can evaporate readily or easily. Like ether, like alcohol, they can evaporate easily. If you put some alcohol on your palm, you notice that they evaporate easily, like perfume. While if you have drops of water on your hand, they evaporate less readily than volatile liquids. So volatile liquids are liquids that evaporate readily. they have relatively weak force of attraction between their particles. Why they are volatile? They can evaporate easily because attraction force is less. Example, ether. In the opposite, non-volatile liquids do not evaporate readily because they have relatively strong attractive force between their particles. Example, molten ionic compounds. If you melt table salt, it's not easy to evaporate. Okay, oil, not easy to evaporate. It's called non-volatile liquids. This figure gives the relation between the temperature and vapor pressure for different liquids: diethyl ether, ethanol, and water vapor. You notice here that for diethyl ether, if you increase its temperature, if you heat diethyl ether, its vapor pressure starts to increase till it reaches here the atmospheric pressure, 762. At this point, it starts to boil, start to evaporate. It boils here, so this is the boiling point of ether, which is 34.6 degrees. At this temperature, its vapor pressure reaches the atmospheric pressure. For ethanol, if you heat ethanol, its temperature starts to increase and its vapor pressure starts to increase till its vapor pressure reaches atmospheric pressure at this temperature, which is 78.5 degrees Celsius. So it starts to boil here. For water, the vapor pressure of water reaches the atmospheric pressure at 100 degrees Celsius. So it starts to evaporate. This is the relation between temperature and the vapor pressure. When the vapor pressure reaches atmospheric pressure, 762, so it starts to evaporate. What's boiling? Boiling is the conversion of a liquid to a vapor within the liquid as well as at its surface. It's different from evaporation. Evaporation can take place at any temperature, but boiling takes place at a certain temperature. When the liquid changes to a vapor at the surface and inside the liquid, within the liquid. And the boiling point, the temperature at which the equilibrium vapor pressure of a liquid equals atmospheric pressure. For example, the boiling point of water equals 100 degrees Celsius. Means what? Means the vapor pressure of water reaches the atmospheric pressure at 100 degrees Celsius. The lower the atmospheric pressure is, the lower the boiling point. If you want to change a liquid into a gas, at lower temperature, you decrease the pressure. Decreasing the pressure, the liquid will start to boil at a lower temperature, like in vacuum evaporator. In vacuum evaporator, it's used to produce sweetened condensed milk without heating the milk. By lowering the pressure, so water starts to evaporate at a lower temperature for milk. And at the boiling point, the temperature remains constant as long as the pressure does not change. As the pressure above the liquid, meaning heated, is increased. Now, if you increase the pressure above the liquid, what will happen? It will boil at the same temperature? No, the temperature of the liquid will rise until the vapor pressure equals the new pressure. And the liquid boils once again, like pressure cooker. The water in the pressure cooker boils at a higher temperature than 100 degrees Celsius. So the food is cooked in a less time. because due to high pressure, the pressure cooker is sealed. No water vapor can escape easily, so the pressure increases. So water boils at a higher temperature than 100 degrees Celsius. And the normal boiling point of a liquid is the boiling point at normal atmospheric pressure. Not less pressure or more pressure. At normal atmospheric pressure, it's called normal boiling point or standard boiling point, which is 1 atmosphere or 760 torr. The normal boiling point of water is exactly 100 degrees Celsius, given the pressure equal to atmospheric. This figure gives the relation between the temperature and vapor pressure for different liquids: diethyl ether, ethanol, and water. You notice here that for diethyl ether, if you increase its temperature, if you heat diethyl ether, its vapor pressure starts to increase till it reaches here the atmospheric pressure, 760 torr. At this point, it starts to boil, starts to evaporate. It boils here, so this is the boiling point of ether, which is 34.6 degrees. At this temperature, its vapor pressure reaches the atmospheric pressure. For ethanol, if you heat ethanol, its temperature starts to increase and its vapor pressure starts to increase till it reaches its vapor. A molar enthalpy of vaporization. What's molar enthalpy of vaporization? To change a liquid into a gas, you need a specific amount of energy. The energy needed for 1 mole is called molar enthalpy of vaporization. So the amount of energy as heat that is needed to vaporize 1 mole, so it's called molar, of a liquid at the liquid boiling point at constant pressure. It's called molar enthalpy of vaporization. The amount of heat, energy needed to vaporize 1 mole of a liquid at a liquid boiling point at constant pressure. The molar enthalpy of vaporization is a measure of the attraction force between particles of the liquid. The higher the attraction force, the higher the molar enthalpy of vaporization. If the attraction force between the particles is stronger, so it needs more enthalpy, molar enthalpy of vaporization. So it becomes higher. The stronger this attraction is, the higher the molar enthalpy of vaporization. Each liquid has a characteristic molar enthalpy of vaporization. It's different from one liquid to another liquid. Water, for example, has unusual high molar enthalpy of vaporization because water has hydrogen bonds between its molecules, so it has higher molar enthalpy of vaporization than, for example, ethanol, ether, and so on.